right, so this is in part based on some recent work with Thomas Kreutzig, Nicholas Garner, and Nathan Gear. We put out sort of a monster paper in December. And also sort of based on various things collaborators and I have been thinking about for the last 5 years or so. There are two questions that I want to discuss aspects of in this talk. There's sort of a physics to math question. Which is what 3D TQFTs arise from topological twists of 3D n equals 4 theories, and in particular gauge theories, are the ones I've been interested in. So 3D n equals 4 gauge theories are the things that Sasha talked about in his talk and that Joel used as inspiration for his constructions in his talk a few days ago. There are other n equals 4 theories that I'll discuss briefly that were studied a long time ago, namely sigma models. So one of the twists of n equals 4 sigma models goes under the name of Rosansky-Witten theory. And Kapustin, Rosansky, and Saulina were the first to describe the extended and necessarily derived TQFT structure that comes from some of these sigma models. But the same package of extended, derived, not necessarily dualizable, so three-manifold invariants may be difficult to construct and require some careful regularization if they do exist, but that same package should be associated to any of the gauge theories that Sasha talked about. The other question was initially much more concrete and motivated this work. In particular, it started out in a discussion with Nathan Gear and Kolya Reshetikin. So this question was, what physical 3D quantum field theories, ideally things with an action and fields, underlie non-semi-simple TQFTs from largely the math literature. And so these two questions will sort of be a long part one and a short part two of the talk. So this part two is also related to recent work of Gukov-Sin, Nakajima, Park, and Pei. So they have a paper a few years ago called Rosansky-Witten theory of Coulomb branches, where they try to answer some similar questions. as I'm about to say, logarithmic vertex algebras start appearing in this context. And so logarithmic vertex algebras have been found on boundaries of supersymmetric 3D theories. Again, in work of Glukhof and collaborators inspired by the 3D correspondence. So in particular, there was work on 3D modularity by Cheng, Chen, Ferrari, Glukhof, and Harrison, so a few years ago, and then some follow-ups. And there's ongoing work of Glukhof, Fagan, and Reshetikin, also trying to answer some of these questions. Just to say there are many groups going in this.
Just a technical remark. You know, for the Zoom people, either they show you next to that board or what you've written on the other board. There is a choice.
Got it? Damn it. I like to walk. Constraints. So part of my point today is going to be that the answers to these two questions are related, and the natural context to look for physical theories underlying non-semi-simple TQFTs is in the world of twists of 3D supersymmetric theories. The one thing that either a feature or a complication of this is that once you move into this world of topological twists, everything is necessarily derived or DG. And so you don't just get sort of TQFTs based on abelian non-semi-simple categories, but you automatically get the full DG enhancement of them. So let me say a few other things and give a few other references. So this idea of DG enhancements or derived generalizations of non-semi-simple TQFTs has also been explored by Christoph Schweigert and Voike and some recent work on things like derived for Linde formulas. And going back a bit further to say what some of these non-semi-simple TQFTs are, prominent sources So in mathematics, one starts often building a 3D TQFT with a braided tensor category that misses sort of the highest level. There should also be a two category of boundary conditions around if it's to be fully extended, but otherwise you can get everything else from this braided tensor category. In physics, it's the category of line operators, and that category has shown up as modules for quantum groups at root of unity. Quantum groups or quantum supergroups. So a prominent source of such TQFTs. Are quantum groups at roots of unity. So semi-simplifying this category of modules for a quantum group leads to the Reshetikin-Turayev construction and to WRT invariance. And that's an old, beautiful story, which is motivation for all of this. So there we have Chern-Simons theory with compact group and integer level related to the line operators, and Chern-Simons are related to modules for the semi-simplified quantum group category, and in turn related to modules for the WZW vertex operator algebra. And that's sort of the thing I want to try to generalize. If you don't semi-simplify, you get something non-semi-simple. So early on, Libashenko and Hennings, I'm not going to write names down. So Libashenko and Hennings mostly defined TQFTs based on these categories. They have this work of Curler and Anna on these categories and the SL2Z actions on their centers which is, so their centers represent a torus Hilbert space, which should have an SL2Z action. Kashayev and Reshetikin then noticed that these quantum groups have a giant center, a Fobenius center, and used that to try to define invariance of three manifolds together with the data of a background classical flat connection. So invariance of pairs, three manifold flat connection. And a lot of this was not, like the Lubashenko TQFT was not quite a full TQFT because some three manifold invariance gave 0. There were a lot of technical and deep issues to be overcome, and a sort of systematic program for overcoming some technical difficulties, also vanishing quantum dimensions and braiding not quite being defined. So a systematic program was initiated by Konstantina Ger and Patiro Miron. And so these are sometimes nowadays called CGP CQFTs. And there's a lot of work by them and many co-authors and follow-up papers over the past 5-7 years. And I'm sorry, that's I think all I have time to say about that now. There's a parallel story on the VOA side. So rational VOAs have semi-simple module categories. Non-rational VOAs don't. And the sorts of VOAs that seem to come up in this story are the nicest possible thing that is not rational, namely logarithmic VOAs. And so there's a great deal of interplay here. The first examples of log VOAs were the triplet algebras by Gabriel and Kausch that were then generalized by Fagan to Poonen. And so they depend on an ADE Lie algebra G and a level K, and one expects that the module category is braided tensor equivalent. Braided. To a suitable category of modules for what's called the small quantum group at a root of unity. And this is now a theorem for SL2, known as a logarithmic Kashtan-Lustig correspondence, and it's a theorem after many years of work. Getting associators correct on this side is non-trivial. I'll throw out a few names. So this sort of equivalence was proposed for SL2 initially by Fagan Gainutinov, Semikatov, and Tupunen before the general G generalization. There were some partial arguments by Nagatomo and Tsuchiya more than a decade ago. And there was a lot of work more recently, Kreutzig, Nulis, and Rupert, and then Kreutzig with Gaiduntinath and Runkel, and Yang and McRae, Lentner and Rupert, work of Sugimoto, and then a very recent paper by Gannon and Negron that finally nailed this down for the case of SL2. But this is hard. Okay, so what I want to come up with, or what I want to talk about by the end of my time, is a very likely 3D QFT candidate, an analog of Chern-Simons theory with compact gauge group, whose category of line operators is the derived category of this. Finally, I should mention that in the supergroup case, so the correspondence between modules for a quantum supergroup and supergroup WZW and supergroup Chern-Simons was also studied long ago by Rozansky and Soler initially. So there are bits that were done many decades ago and bits that are new. Okay, let me talk about 3D n equals 4 theories. Sorry, I keep moving. Place some graduate students on either side. Push me back. I'll use the letter T to denote a general 3D n equals 4 quantum field theory. So this is a QFT with a lot of supersymmetry. They come in many different families. Two prominent ones are gauge theories. They're labeled by the data of a group and a symplectic representation, as Sasha said. For me, the symplectic representation will be T star of just some complex representation. So maybe I'll just have, this is not super important at the level of this talk, but I'll have G acting on T star V. There are also generalizations of this, given some very special constraints on the matter representation. There are generalizations that allow Chern-Simons terms, or Chern-Simons levels, which at the moment falls out of the realm of, say, a BFN construction, but it would be nice to.
Can you say what the constraints are?
Yeah, so if you want to take a theory like this and additionally gauge some extra symmetry G tilde, say a symmetry of the hyperkähler quotient, or the symmetry of the quotient. The moment map needs to the moment maps needs to be isotropic, I think is the word, but using the Cartan pairing on the moment map, mu has to be 0.
Which moment map is it?
So it depends what sort of topological data you're trying to extract. If you want to topologically b-twist this, it's the complex moment map that matters. So,
but it's a moment map for which group, first of all?
Oh, for G tilde.
Tilde on the quotient.
On the quotient.
And the condition is that you're saying that.
Yeah, this needs to be isotropic. So this is from work of Gayotto and Whitten.
With respect to which pairing?
Sorry?
With respect to which pairing?
The Cartan pairing on the Lie algebra of on G dual of
What's Cartan pairing?
So in order to define a Chern-Simons term, you need to choose a bilinear form.
Okay.
And it's the inverse of the bilinear form that is being used to contract the moment map. This Chern-Simons generalization is important for what I actually want to discuss in the application. And then there are sigma models that I mentioned. That are labeled by a smooth hyperkähler space. If you want to do algebraic stuff with it, a smooth algebraic symplectic. Variety. any such 3D TQFT, any up to some anomaly issues that I don't want to get into, it admits two topological twists. There should be two ways to extract a TQFT functor from this data. Starts with a T, and these two ways to extract a TQFT functor are called A and B twists. And I'm calling them this in direct generalization to what happens in 2 dimensions. There are A and B models in 2 dimensions defined from the same initial data. I'll call the TQFT functors ZA and ZB. The B twist, as I mentioned before, in the case of sigma models, is called the Rosansky-Witten twist. In gauge theories, it was previously described by Blau and Thompson. The A twist was not really new to 3 dimensions. It's a dimensional reduction of Witten's Donaldson twist. And so in particular, in abelian gauge theory with where G is C star and V is C, this is related to 3D Seiberg-Witten invariance. So one expects these to be extended. Expect, this is before, sort of a maybe 3, 2, 1, 0 extended TQFT. The 3 I put in parentheses because there may be issues in getting finite 3-manifold invariants. So let's say they may not be fully generalizable. And there are 2 of them. To connect with Sasha's talk, so a 3D TQFT associates to the 2-sphere an algebra, and this algebra is what Sasha called in the A twist functions on the Coulomb branch, and in the B twist this algebra is called functions on the Higgs branch. Another nice feature that's parallel to the 2-dimensional story is that often such n equals 4 theories come in pairs. That are related by physical duality known as 3D mirror symmetry. And given a mirror pair like this, the expectation is that the TQFT functors will be equivalent up to an exchange of A and B. So ZA for T, ZB for T dual, whatever the dual theory in the pair is, and similarly for TB.
Well, I think that 3D mirror symmetry is automatic, right? I mean, it's just the only question is whether they can describe the dual theory, but the existence of dual theory is just take the same theory and just twist the action of the sort of bunch.
Sure, but that assumes you're describing it as a CFT. So to the extent that you can get anything out of the CFT data, yes. Right. So mirror symmetry was formulated in terms of infrared CFTs. And there's an obvious Z2 involution, the same as happens in 2 dimensions that induces this. I would say the interesting case is when you know that there are two different, say, gauge theories that will flow to the same CFT up to a Z2 involution. Yeah. So when I say often, what I actually mean is we often have pairs where T and T dual are both nice. They are, say, labeled by the sort of data I described here, a group and a representation or a smooth space or something like that. And I don't think this is true in all the time, but there are many examples.
Sure, just typically if you start with nice T, the dual theory will probably not have a Lagrangian description in general.
Yeah, exactly, and all of these.
But I'm just trying to say that if I understand correctly, formally its existence is automatic. So
It's just formally I agree. So this sort of statement is what ought to be called homological 3D mirror symmetry. Just to give an idea of what it will entail, actually understanding or perhaps proving, reducing these sorts of statements for suitable T and T dual on an interval or a circle should encompass all known statements of 2D homological mirror symmetry. So this is independent. Well, it's sort of it's a stronger statement than 2D homological mirror symmetry and categorifies it. But like this is already extremely hard. I find it very interesting to try to even come up with examples of extended TQFT equivalences like that in 3D. The final thing I want to say, an ultimate thing I want to say, is that these 3D theories, that's it. Real quick, the bucket. Thank you. These 3D n equals 4 theories often have large symmetry groups.
Oh, you need to write.
I see. And so I should erase the one underneath first. And then maybe wait to...
Yeah. No, well, I mean, of course, waiting is an option. But
Oh, squeegee. Got it. Sorry. Yes. It's been a while. Thanks. I'll get the next one. All right. Right. So also often there are symmetry groups acting on 2D n equals 4 theories. They come in two types. There's Higgs symmetries and Coulomb symmetries in a gauge theory description. A Higgs symmetry is something that acts on the quotient, preserving, it acts as via Hamiltonian isometries. On the quotient, and if we have such a symmetry, then the corresponding topological twists are enhanced or deformed by connections for this gamma symmetry group. ZB can be deformed by flat gamma connections. And ZA gets deformed by gamma monopoles. There are some generalized monopole equations that these connections need to obey. And then there's the mirror statement. There are other kinds of symmetries that one sees as acting on Coulomb branches in a Hamiltonian way. And then for these other symmetries, ZB, one gets the mirror statement. So ZB is deformed by monopoles. ZA is deformed by flat connections. What I mean by that, so these TQFT functors take any manifold of dimension 3 or less and associate various algebraic objects. What I mean by deformed by, say, a flat connection, is that you take the data not just of a 1 manifold or 2 manifold or 3 manifold, but that manifold together with a choice of flat connection. In the monopole case, it's a 3 manifold with a monopole configuration. For a surface, this just boils down to an algebraic complex connection on the surface. So these TQFTs sort of get fibered over spaces of connections. The final thing about these 3D n equals 4 TQFTs was explained by Castella and Gaiotto. A few years ago. The twists, sort of the twisted 3D theories admit boundary conditions. They're not topological boundary conditions. They depend on the choice of holomorphic structure. They admit holomorphic boundary conditions that support VOAs. In principle, giving one access to the same package of relations that exists in the Chern-Simons WZW relation, where, for example, the module category of these VOAs, or of a boundary VOA, should be equivalent to Z of S1, to the category of line operators in the 3D theory, and conformal blocks, though in this case derived conformal blocks, of these VOAs should be state spaces of the 3D theory. And so on. These are typically logarithmic. In fact, in all the examples I know, they are logarithmic.
Sorry, is there some understanding why these are specifically logarithmic?
No. I don't have a deep one. And maybe even like logarithmic may not be the right word. One needs to use some properties of the module category to describe what's going on, and there are likely some statements to be made given expectations from 3D, but I'm not totally sure. They're not C2, so they're not always C2 cofinite. That's sort of the obvious restriction that you would impose.
How is it the rational ones cannot come up?
Oh, sorry, rational ones can come up as in special cases. Sorry, they're very generically they're not, but one can engineer examples that are just ordinary Chern-Simons theories, or they're equivalent to ordinary Chern-Simons, and then you'll get something rational. Totally. Okay, so I want to do a simple example. So T is going to be what's called a free hypermultiplet. Physically, in other words, it's a gauge theory where the group is trivial and V is C, or it's a sigma model where our complex symplectic space is T star of C. And I'll consider the B-twist. And rather than overloading the notation, I will just call the B-twist of this Z rather than ZBT. In order for this TQFT to be Z graded, sorry, I also go back and forth between Z and Z. I'm very confused for the past few years. So in order for, gradings are obviously Z gradings. So in order for this to be Z graded, one needs to shift the grading of the structure sheaf on T star C. So the fancy derived geometry way of saying this is that we're actually going to be looking at the two-shifted cotangent bundle of C shifted by 1. What I actually mean is that this is spec of a polynomial algebra and two generators that each have degree 1. X is on the base, and Y is the coordinate on the fiber. These are bosonic. It's a standard commutative polynomial algebra. It is completely weird that they're an odd degree, is what happens in these theories. There's also a symmetry.
So does it mean that the Z grading is not coupled to the Z mod?
Indeed. So there's an additional Z mod 2 grading that determines signs. Exactly. There's a group that acts here. Symplectically is just SP2 as you see. And that group in the B-twist will lead to everything being deformed by flat SL2 connections. So
you say flat SL2 connections, it's flat SL2 connections where? On what?
On whatever you're applying the TQFT functor to.
Okay. But is it a statement in dimension 3 or in all lower dimensions as well?
No, in all lower dimensions. So,
that means, dimension 1, for example, you're supposed to get a family of categories
over
over
the Durand-Rigetti space of a punctured disk. Yeah, absolutely. Okay, so I'm just going to list some things. So Z of S2. This is functions on the Higgs branch, which in this theory is Higgs branch is T star C. Z of S2 is the underlying vector space. Well, it's this algebra. It has an algebra structure from 3D pairs of pants. C of xy. And the thing I want to point out immediately is that this is not C. which you would expect in a well-behaved TQFT, that you can just cut out a solid sphere and not do anything to your 3-manifold. When usually wants the Hilbert space of the 2-sphere to be C. And it's not C, it's not even finite dimensional. But if we think of this as a graded space, it is C in degree 0. And then C2 in degree 1, and C3 in degree 2. And I may have my shifts off by sign, but so in terms of the algebra, if we just look at homogeneous polynomials of a certain degree, and remember that x and y are in degree 1, this is a space with finite graded dimensions, where the 0th graded piece is C. That's the TQFT C. That is more familiar. This is what one has to deal with in the derived world. Z of S1. So also here, there are no flat connections, just because S2 doesn't have any non-trivial ones. So Z of S1 should be a braided tensor category. And Kapustin, Rozansky, and Salina identified this as derived coherent sheaves on, if we're careful about gradings, there's some shifts in there, but I'll just say T star of C. This is a braided monoidal category where the monoidal structure is deformed by the holomorphic symplectic form on T star C. The identity object is what you would call Z of X. It's identified as the structure sheaf. Its naive tensor product with anything acts as the identity. And just to double check that we have things right, so if we look at derived endomorphisms, really, it's the structure sheaf, it doesn't matter whether you do derived or not. Endomorphisms of the structure sheaf, of course, in sort of a stupid way, just give you back the algebra of functions on the space, which is correct. So this had better be what the TQFT assigns to a 2-sphere. If we introduce a flat connection on the circle, things get more interesting. And so to do that, algebraically, one needs to introduce some algebraic structures. So for a flat connection, I'll replace S1 with, say, a formal punctured disk. And I just want to give an example of what happens. So if we take a connection that has a simple pole, and the residue is small, then Z of S1 with this connection becomes matrix factorizations on T star C with a superpotential given by the moment map contracted with whatever that matrix is, which for a diagonal connection looks like alpha xy, where x and y are coordinates here. These are Z-graded matrix factorizations that can happen when the superpotential has degree 2, which it does. And you might say, okay, well, this is a stupid matrix factorization. When the superpotential is quadratic, this trivializes. And indeed, so if alpha is generic, here just non-zero, this becomes vector spaces, and in particular semi-simplifies. When alpha is 0, this reproduces coherent sheaves.
Could you recall what are those matrix factorizations?
Not in the time I have. Sorry.
You can say it in one word. It's just complex such that square of the differential is not zero, but whatever is equal to this alpha xy.
Yeah. Thanks, Sasha. This description manifests the family of categories as a coherent sheaf of categories over, in this case, been using a Durham-like description, but we've got a coherent sheaf over flat gamma connections on a punctured disk. And if we look at connections with regular singularity, that is complex isomorphic to just the group itself, gamma mod gamma. So we get this family of categories that Sasha was referring to. The fiber over the identity is really interesting and derived. It's the derived category of a non-semi-simple thing. All of the other fibers, generic fibers, not quite all the others, but generic fibers become semi-simple and in fact trivial here. I think I want one or two more things about this example. And while I erase so what is a matrix factorization? It's a coherent sheaf on an affine space is a module for the algebra of functions. A matrix factorization on an affine space is a complex of modules for the algebra of functions with a dimorphism of degree 1 that squares to the superpotential. That squares to this x times y thing. And so if the superpotential is 0, one just recovers coherent sheaves. And if the superpotential has non-degenerate critical points, the category trivializes and just becomes a sum of vect on the critical points. There's a vertex algebra involved. The vertex algebra here rush job. The vertex algebra for this example is symplectic fermions. So this is a VOA that's strongly generated by two fermionic fields, psi and chi. Sorry about that. With OPE that is that has a quadratic. And modules for this modules for this algebra are completely induced by modules for the zero modes. So modules for this algebra just look like modules for two fermions for an algebra and two anti-commuting generators. And how does this at all look like coherent sheaves on T star C? Well, if you look at graded sheaves, which I should have said earlier, we want to respect this Z grading. This is the derived category is Koszul dual. So the abelian categories have no relation, but the derived categories are equivalent. And this is like another sort of really basic place where nothing works unless you're in the derived world. Okay. The VOA, the symplectic fermion VOA, has the same deformations by flat connections that are described in the category. Given a flat connection on a formal disk, one can deform the OPE. With a first order pole. And we'll just say it in words. So that deformation for generic connection with a first order singularity deforms this VOA to two copies of free fermions, which has a trivial module category. And so the same sort of feature where the category is fibered over flat connections and semi-simplifies, trivializes at generic connection, appears from a VOA perspective as well. All right. I think that is all I have time to say about this example in order to leave any time for the actual thing. Yeah. Okay. So let me say what we actually did. So the interesting example. If you take G to be SLN and consider quantum SLN at an even root of unity. So this has what I call the Fobenius Center, another use of 0Z, Rob, generated by Kate Powers of the Chevalier generators, Serre generators. And it is well known that spec of the Fobenius Center is an algebraically open subset of, for even root of unity of the Langlands dual group. So Langlands dual group I will call gamma. When algebra has a center, the category of modules fibers over the center. So the QFT mod C fibers over gamma, or more accurately, over an open part of gamma, containing in particular the identity. The fiber at the identity, right, and so, sorry, and I'm requiring, not saying it, I'm requiring this center to act semi-simply on modules. The fiber at the identity is what's known as modules for the small, or restricted quantum group. This is a non-semi-simple category. Generic fibers are semi-simple, and there's a stratification of the group on which you get more interesting things in between the huge non-semi-simple thing and other semi-simple fibers. So this category was used to construct a whole host of knot and three-manifold invariants. We mentioned ADO invariants before as well. And I said before, so there's a relation to Feigen-Tipunen algebras. So this we expect, one expects in general, that this is equivalent to modules for the Feigen-Tipunen algebra of G at level K. And it's proven when G is SL2 and the Feigen-Tipunen algebra is the triplet.
The Feigen-Tipunen algebra is what? I'm sorry. You said it's proven for SL2, and is that something about
when G is SL2, the Feigen-Tipunen algebra is the triplet.
Is what? I mean,
the triplet VOA.
Oh.
It has a special name, and it was one of the first
It's still logarithmic.
VOAs to be described. Yeah.
It's still it's not a nonce VOA. It's
yeah, no, it's logarithmic. It was like it's the first interesting example of a log VOA from 3 decades ago. Yeah.
And so it's known to be equivalent to this UQG modules for all K.
It is with a suitable modification of associators. So just describing braiding, the braiding on the two sides naively does not match. And one needs to fix that, but yes. So what we expect is that this generalizes to an equivalence in all fibers, where the Feigen-Tipunen algebra has a big G-dual symmetry, and has an OPE that can be deformed just like this. So one would expect, and we know how to do it for the SL2 case. Expect that there are deformations by flat connections, such that the deformed VOA modules match other fibers of this quantum group category, where G is the holonomy of a flat connection with simple hole. And as I have hit the end, I'll use right down our main conjecture. Conjecture may be kind of obvious. So there exists a family T and K of here n is greater than 1, K is greater than n, of 3D n equals 4 theories. Such that there, in this case, the thing that's relevant is their A-twists, such that the braided tensor category associated to the circle in the A-twists of these theories is the derived category of UQG at a
Is this capital U small?
It's capital U, and it's circled with in the presence of flat connection. So this is they're both. I think there's some algebraic structure issue, but they're both sheaves over the Langlands dual group. So I should say something else. So what property do these theories have? So first, the Langlands dual group acts on them. PGLN acts as a Coulomb type symmetry in this case. which is the right thing to give deformations by flat connections. So the quantum group category fibers over the Langlands dual group, and so does the category of lines in these theories by the mechanism I explained before. Defining the theories, I don't think I can do it in a way now fully that's going to make a lot of sense, but I will say what they are approximately. So T and K in the A-twist is approximately Chern-Simons theory for SUN at level K minus n, tensored with Rosansky theory on the twice-shifted cotangent bundle of the flag manifold for SLN. And so this is not exact. Like these two talk to each other in an interesting way, which is what makes this nice. But one can, using this very approximate description, one can compute and match things like some state spaces. The reason we actually believe, I think the strongest reason we actually believe this conjecture is because physically we can make an argument that this family has Fagan-Tipunin algebras on its boundary. It has the right boundary VOA to fit that side of the story. And I think, like, at least that for me completely nails it. In addition, one can do various other computations and checks and hopefully compute some things using these theories in a new way that was not obvious from, say, the quantum group side. Sorry, I must stop there. Thank you.
Cool. Let's thank the speaker. Are there any questions from the online audience, maybe, to begin with? Let us see the chat. Are there any questions from?
Yeah. How do these two theories? You said they're talking to each other. How do they talk to each other?
So the way this is defined is by it's still going to be somewhat schematic. So how do you get this T and K? Well, you start with a standard sort of n equals 4 gauge theory that has it's a quiver theory defined by some matter and some gauge group, and roughly applies Sasha's construction. But sorry, so you start with some T prime, whose Higgs and Coulomb branches are both nilpotent cones. This depends on n. They're nilpotent cones for SLN. This has two symmetries acting. There's, depending on how you look at it, there's an SLN acting on one of these, and there's a PGLN acting on the other, and it's not at all obvious why one is SLN, one is PGL. Then we take one of these symmetries and gauge it with a Chern-Simons term. That's the coupling. So you start with something that has an action of SLN, and then we gauge that with a Chern-Simons term and define standard Chern-Simons theory, but it's Chern-Simons theory with matter, roughly nilpotent cone matter. And that's how they talk. So we gauge this. We gauge the SLN at level K. That's T on K. It still has a PGLN symmetry that we've done nothing with, and that this other PGLN symmetry is where the flat connections come from.
questions?
Is there any reason why you do this for SLN and not for arbitrary?
Yes. It's so this side of the story makes sense, of course, for arbitrary group, as you know. I find the matching with quantum groups to be very confusing. When you're in other type, the structure of UQG mod as a sheaf gets complicated. You don't necessarily, I would expect that you always get the Langlands dual group, but I don't see that.
That's not true. That depends on K.
Exactly.
Actually, even in type A, that depends on K. I think. Because
well, so it does
you get something, I mean, you always get a group whose Lie algebra
exactly.
is, but then sometimes it will be a PGLN, sometimes SLN, sometimes something in between, so that
Yes.
really depends on.
So there are global issues that at least I don't fully understand yet.
So I think even in your case, somehow this issue is there.
Sorry, I think you're right. So the root of unity is always even for me.
Okay, that's
so that's
a convincing. That probably takes care of that.
When the root of unity is 0 mod 4, there are still some spin issues around to deal with, and there are still subtleties even there. But yes, sorry. So there should absolutely be a statement for general group.
But even in type A, so you actually need some assumptions on the order of the root of unity, right?
Yeah, absolutely, and things will depend strongly on that. And yeah. So I fully expect something, but I don't know how to pin it down yet.
And also wanted to ask about this reflection about Factorization algebras modules over there being models with a small quantum group. So can you somehow see a functor, so sort of, I mean, you have a restriction functor from the big quantum group to the small quantum group. And modules over the big quantum group you can also realize in VOA language. This is basically a Scarjan-heuristic equivalence.
A generic Q.
No, for any Q. It works for any. Scarjan-heuristic equivalence works for any Q.
Okay.
Maybe also some sense that some roots should be even or something like that. I mean, actually it works for any Q if you formulate it correctly, but essentially it works for any Q. So the question is, can you see this restriction functor in the language of VOA somehow?
So likely, but I'm not sure.
I mean, on the language VOA, one is not a sub-algebra of the other anymore.
No, it's so to demystify Fagan-Tikkun a little bit. One useful thing to say about it is that this is an extension of W algebras at level 1 over K, tensor with finite dimensional modules. I think it's for PGLN in this case, and that so you may be able to start seeing what's happening by looking at W algebra representations. But I don't think I can do any further justice to your question. There are a lot of things I still don't understand in the VOA set, and I would ask generally Thomas Kritzig about all these things.
Other questions?